Welcome to the lecture series on Similarity Modeling 1 and 2, Seeing and Hearing in Computers. My name is Horst Eidenberger. This lecture block is on perception and psychophysics. The educational goals of today are threefold, as most of the time. First, it is to understand the basics of perception and of the brain processes behind perception. They're very complex, there are many important terms. It is not well understood today how they interact with each other. So I don't expect you to keep all the details that are going to be mentioned in the lecture, but you should try to understand the big picture, or if you already know the big picture, try to augment it by a few more details. Okay. Since it is a knowledge-based lecture, today's lecture is a bit different structurally. Most of it comes from prepared slides that I'm going to show and that we're going to work through bit by bit. All the slides can also be found online in the TU Wien e-learning platform. They are linked as PDFs. All slides that were not done by me are either referenced by the student, or if not, a few slides also come from the book Kandel, Schwartz et al. Neuroscience. I will point it out whenever I use something that was not done by me. Okay, so the first goal is to understand these enormously complex processes, at least a bit. We have only a small time frame, so we cannot go into much detail. But still, we should be able to manage the most important bits. Second goal is that you understand what psychophysics is. This is an old term dating back to the 19th century. It is very important in our everyday life. There would be no Zoom conference without the use of psychophysics. However, only few people know about it, and you should understand the fundamental laws, how these laws were defined, and what they describe about perception processes and how we actually filter information when it enters our brain. And the third goal is very specifically in the area of psychophysics. You should be aware of the most important psychoacoustic transformation, in particular going from sound pressure to loudness, going from perceived highness of the sound to the actual pitch, and going through the critical bands, that is, dealing with masking out of sounds. These are our goals. As always, if you have any questions, please ask in the forum, state your questions there in order to trigger a discussion on the topic. Okay, as I said, it's a bit a different lecture. There are many pictures here. This one comes from the slide set on psychophysics. It is a very old one, dating back to the early 2000s. Still, the data is mostly valid. Yeah, let's go through it. It should provide you the next two. This one and the next two should provide a little bit of an introduction in the field of human perception. The most important thing is we have a plethora of neurons, some 10 by the power of 10 neurons. That is apparently a lot, 10 billions. And the number of synapses is even bigger. Maybe today we have to use the chalk more lightly. We have 10 by the power of 13 synapses, that's 10 trillion. That is a huge number of objects considering the small size of the human brain. It means that we have hundreds of thousands of neurons per cubic centimeter alone. So the size of a dice contains hundreds of thousands of cells. If you think that these cells are rather complex and have co-firing patterns, so being covariant on each other, this creates an enormously complex field for information processes. And as you know, that the fundamental operation in a neuron is an act of convolution. it means that we have a very complex measure here for pattern recognition and similarity modeling. Okay, so how does it grow? It has not been fully clarified so far how growing of the human brain actually works. Apparently, the number of neurons increases exponentially in the early years, in particular to the age of 2 or 3 years. But that, of course, is very different between the individuals. It's still growing, but with decreasing speed up till the age of about 12. Always take these numbers with a grain of salt. It really happens, it depends on the individual, what actually goes on. Interesting enough, though, this growth of the neurons tends to become slower and almost stop with age. However, what does not stop, as far as we know, is the growing of new neural connections. Two neurons can be considered to be connected. In most cases, there are of course different types of neurons. We cannot go into these fine gradations in the short time frame that we have. If there are like 200, 250 connections between them. So it's not just one connection from a synapse to a dendrite. It is an enormous amount of parallel connections between two neurons that actually establishes a expressive connection between them. Okay, in average it was counted that a neuron is connected to 3% of its neighbors. And that concept of neighborhood, I think, is very important. Neurons are mostly connected to their neighbors. They are not so much connected to neurons in completely different areas. That necessarily creates a layer structure. These layers are often called centers. That is a fundamental physical, not limitation I would say, but feature of the brain that we have to keep in mind. So if we apply, for example, electrodes of an EEG on a particular neighborhood, then usually we do not learn anything about the functionality of the neighborhood, but record all the action potentials together. Which of course gives us a very limited possibility for predicting something from an EEG. So what you often read in the newspapers is highly exaggerated. Okay, action potentials are somewhere between 50 and 80 millivolts, so not very high. And the neural activity is about 2 milliseconds, very, very short. If it was a purely electrical connection between synapses and dendrites, it would of course not been weighted, but it would also be faster. There are such electric connections between neurons, for example, when it comes to reflexes, which are mostly located in the older parts of the brain. The frontal lobe and then all the more recently developed, evolutionarily more recently developed areas tend to contain neurons that are not electrically connected, and that means that the neurotransmitters also delay the propagation of information from one cell to the connected cell over these hundreds of connections between the two to an average of something like 10 meters per second. Of course, these are average numbers. In such a huge area as the brain, the average usually doesn't say very much about the individual neuron. Okay, so if we need 200 connections, then we will, of course, per synapse not have a very high contribution. When we go through the nerve cell after this first introduction, then I will show you where the actual processing happens. It's essentially a process of 1, 2, 3, 4, 5 steps. The closer a synapse binds to the axon hillock, the more influential it is, because this is where the firing happens. An average weight is somewhere between 1% or at the most 5% of the individual neural connection or the synapse. So scholars have computed the perceptual load, so the amount of data that enters to the eyes, the ears, the gustatory, olfactory, and haptic senses, and it is approximately a gigabit per second, which is a lot. So that is roughly 1,000 stimuli of different tastes, different smells, different sounds, and visual objects, visual events that happen at the same time. So how do we deal with that? I've learned that we throw away like 99% of the data. And some of the data that has been thrown away in the process is later reconstructed in later stages of the visual processing. We will come to that when we have a look at the visual system, where I rely on slides that were done of one of my students in a seminar. And then I would like to show you what the individual processing steps actually are. One very important concept in the brain is adaptation. If you want to learn more about it, come to Media and Brain lectures in the summer term. Adaptation means that the repeated application of a stimulus on the brain over the perceptual system, and that is the interface to the outside, the sensor interface, will cause a decreasing response. So at the first presentation of a stimulus, the reaction should be strongest. Over time, it should get weaker or fade out completely. That is very important, in particular if you want to find out something about the brain through studying, through presentation of test stimuli and watching and observing the reaction of test subjects. Okay, so what have we learned? Perception has a layered structure. We have this neighborhood concept, and it's based on attention. So we find out something about the environment. Attention means, paradoxically, maybe paradoxically, to throw away 99% of what comes along and process in detail the rest. Okay, let's go on with this. So what senses do we have? We have apparently the oral sense, the gustative, the haptic, olfactory, and vision sense. And here are also given the number of approximately of nerve cells that we have. Particularly interesting, in my opinion, is that not vision is in numbers of neurons is our biggest sense, but that is actually the olfactory sense, because we require all these nerve cells in order to distinguish the different smells in the smell bulb. For I think somewhere between 5,000 and 10,000 different smells that we can distinguish, we need these cells, and they are partially highly specialized for the task. Vision is also very, very big. This contains all of the receptor cells for brightness and for the different color channels. We also come back to that again. We have an Rgb system. Very interesting, at the other end we have the sense of hearing, which comes along with a few 10,000s of nerve cells. That is because the processing in the mechanical part of the ear is so efficient that we actually need very few nerve cells to propagate the oral sense to the brain. I will explain you in detail how it works. This is our third educational goal of today. Touch and taste are somewhere in the middle, with hundreds of thousands of different nerve cells. The haptic sense in particular is very complex. In the layer structure of the skin we have different receptor cells for vibration patterns, for shock, for different forms of touch, of pressing, so it's very, very complex. And also we have loose nerve ends for the recognition of injuries, for example. Okay, taste distinction is mostly salty, sweet, sour, bitter, and yummy, as it is called. So in particular, very good or not very good is relatively limited in the human being. When it comes to the visual sense, the one important aspect that you might want to keep in mind is that the relationship between rods and cones is 20:1. What does that mean? The rods are responsible for brightness. The cones are responsible for the Rgb perception. Having it 20:1 in general means that our resolution is for brightness 20 times higher than for color perception. However, most of the cones are located where it matters, in the so-called fovea, in the background of the eye, where we can really see sharply, where the focus of the lens actually goes. The rest of the retina is mostly stacked with rods, and that means we have a good peripheral seeing of brightness changes, but not of color changes. This relationship of rods and cones is one of the reasons why in art some photographs still do photography work with black and white film, so that the resolution in the camera and on the film material becomes better perceptible through the capabilities of the human beings to distinguish brightness. Okay, what else is important? We come to the different types of cones in a minute. There's a particular problem when it comes to distinction of red and green. I will show you that. You might have heard of red-green blindness, or might suffer yourself from this condition. And scholars say that the reason for that is the very recent, evolutionary scene, very recent development of the red cone, which is, so to say, a spin-off of the green cone and moving away lightly. Green, of course, the distinctions of shades of green is easily imaginable to be important for early mammals in millions of years ago, living in forest conditions or savanna conditions. It's of course beneficial if you can distinguish different shades of green from, for example, a predator that is non-green. And distinction of red is something that for us today is of course very important if you just think of traffic lights. Evolutionary, however, this is very recent. Okay. So another thing that we will have a look at are the first stages of processing through the ganglion cells. I would like to postpone this for a second. Yeah, as I said, the fovea is very, very small. This center part where we can have the sharp seeing, it's just 1% of the whole retina, but it is mostly consists of cones. So color seeing is where we actually can see very sharply, and since we can move the eye, we can do a color scan of our environment all of the time. That is referred to as saccadic seeing. If you do something in human-computer interfaces, you might do experiments with an eye tracker, and that is essentially for recording the saccadic movement of the eye muscles, which is an autonomous part of the brain. And yeah, we will also see in a few minutes that there are specialized layers for edge processing, blob detection, orientation detection, and so on. Okay. Most important maybe of these aspects was that in comparison to other senses, the oral sense is highly efficiently coded because the mechanics do a lot of work in there. We have an optimal hearing at about 4,000 hertz, 4 kilohertz. That is because our speech mechanisms, usually as a source filter model, can produce sounds of up to those 4,000 hertz. I told you in an earlier lecture that the cheapest protocols like old-fashioned telephone and even the first generation mobile phones, GSM, would use 8 kilohertz for the codec as the upper limit of the sampling. According to Nyquist and Shannon, the sample rate has to be double the maximum signal that is to be expected, since we human beings can create sounds of approximately 4000 Hz at the most. 8 kHz should suffice, of course without trained singers, should suffice to cover the entire range of speech in a signal. Okay, we will also come to the sound pressure level. The important thing about it is this is a relative value. Sound pressure level means to compare the pressure that you have at the moment through a microphone, through a typical microphone for sound recording, to a reference sound. And by dividing the actual sound level to the reference sound, we lose the unit, and therefore it is usually written in bell, because bell is a unit for those numbers that don't have a natural unit. And since we employ a logarithm on the base of 10, it is usually called a decibel, or short decibel. So what we have when we have sound pressure is we have a logarithmic value with reference to one particular well-defined sound of 1 kHz. Okay, that is very important. If you're interested in that, have a look at the ISO norm 226, where it is all defined. This is one of the few norms that are actually more or less available in public. Okay, we will also come to the propagation with the hair cells. That is the mechanical part that I spoke about. That is now not so important. Sensory pleasantness, it was defined by Fastel and Zwicker as how sharp is a sound, how rough does it appear, how loud is it, and is it harmonic or not harmonic, is an interesting aspect when it comes to feature design. And one other interesting feature is that depending on the frequency of the sound, we rather tend to hear it in front of us, behind us, like 10 kHz, or 8 kHz rather on top of us. Okay, so much on the fundamentals of perception. Before we go into the area of what the different senses actually can do, I would like to do this brief introduction into psychophysics. It all started in the 1830s, I believe, when two German physicists, Weber and Fechner, I believe one of them working in the optical industry, the other one also being a notable physicist in the area of electrical engineering, started to investigate the relationship of what they measured on the physical side, which they called phi, in comparison to what humans actually perceive, called psi. This relationship, it turns out to them, was not a linear one. So as human beings in our brains, we don't actually perceive the world as it really is. But they said, ooh, this is rather a logarithmic relationship. Meaning that the physical amount, the physical amplitude arrives at the logarithmic scale in the perceptual world. So the Weber-Fechner law states two things: that what we perceive is kind of logarithmic with some weight of what is actually going on, plus some constant, usually denoted as A. That is called the Weber-Fechner law. And it held for a very long time because it is particularly good to describe the processes of hearing that were well investigated and early investigated, because it's relatively easy to provide stimuli, to measure the sound pressure, and also to measure the perception of human beings in terms of loudness, for example, or pitch. Okay, there is also the Weber law. The Weber law alone said that the delta of the physical stimulus is a function of the physical stimulus, meaning that with increasing signal, with increasing stimulus, also the changes have to increase in order to be perceptible. That is called the Viva Law. And it is a formulation of this rule of adaptation, if you will. The first presentation of the stimulus will be more recognized. If you want to have the same level of response, you have to increase over linearly. Otherwise, you will lose it. Okay. In the 1940s and 1950s, more and more psychophysical analysis work was done that identified rules other than the Weber-Fechner law. So they would violate it. Sometimes it would not be logarithmic but linear, the relationship between stimulus and psychophysical response. Sometimes it would be even over-linear, in particular for electrical shock, for example. We will see a few examples on the next slide. So a new law was defined by Professor Stevens, and that said what we actually perceive is what we had with the contents of what is actually going on with an exponent A. And this one is called Stevens exponent. And the whole thing is called Stevens power law. That is something you should try to keep in mind, because it is very handy and very, very helpful. So if you pick bits from today's avalanche of knowledge that comes in the lecture block and try to memorize something, then keep Stevens power law in mind, because it explains a lot of things. And it also well defines the process, because nowadays psychophysics to a degree means identifying the exponent for different domains. How is that done? By looking for so-called just noticeable differences. So test subject will be presented with different stimuli, either visual, oral, gustative, haptic, whatsoever. And the investigator will look for an increase or a decrease in the amount of stimulus that is presented, that remains unnoted, and he or she will make a recording whenever the test subject says, I recognize a change. And from that data, it is possible to compute the curve for this particular stimulus. And with that curve, it is possible to approximate it through setting the parameters A and, of course, the always weight C, and there might even be a B, meaning an offset, a bias for the entire function. So these parameters can now be found in a well-defined process without having to make additional hypotheses on the form of the curve. That is Stevens power law, the fundamental rule of psychophysics. Keep in mind that the whole domain is about what is physically going on and how we perceive it as human beings. Because the fundamental truth is that the brain is locked in. The physical world happens around it. And in between, we have a layer of chemoelectrical signal propagation. What arrives in the brain, that is for sure, is a sequence of electrons. What happens outside is a multitude of different forms of stimulation, some chemical, some physical, that only arrive in the brain as electrical signals. Okay. Having had a look at that, let's see what types of exponents Stevens would identify, and others as well. I already told you that the most unpleasant thing in the list that I found in the book of Gscheider, there is Fundamentals of Psychophysics. Which is essentially their book in this area for learning the fundamentals. So electroshock is the most unpleasant thing there. It is apparently not logarithmic, but highly exponential. What does it mean? You stimulate with something physical and you show a psychological reaction on that. And stimulating somebody with electrical shock is first not noticeable. Then comes the threshold of the just noticeable difference. And then it becomes almost immediately unpleasant. So the reaction is very strong and it is a negative reaction, unpleasant. Nobody would react positively, I believe. Okay. Another thing that is overlinear is muscle force. So the strain that you feel when you have to use your muscles in order, for example, to lift the weight, that of course has to be well defined in the stimulation, in the experiment, is also something that goes overlinear. That means our ability to actually use our muscles is very limited. We are very quickly overtaxed by a particular stimulation. If it was logarithmic, we would be more enduring, meaning that you increase the weight and increase the weight and increase the weight, and we still can do it. We still don't perceive a difference that is, in this case, again, unpleasant for us. Muscle force is effortful and therefore rather unpleasant normally. However, it is the other way around. So whatever you do and however much you go into the gym, in the event, you will have to give up at some point because it increases overlinearly. Okay. Something very close to a logarithmic scale, to a linear scale, is the perception of warmth. That means some warm stimulus is provided, for example, on the palm of the hand. And if the temperature is increased until it becomes noticeable, the question is, how strong do we react? We react more or less linearly. Only at some point where it becomes really hot then from warmth, it becomes unpleasant and overlinear again. Tricky thing with human beings is the perception of coldness versus warmth. Coldness is perceived much less than the perception of warmth, and that comes with a fundamental problem. If you live in a colder climate, of course, then since you don't recognize it, that there is a significant difference in the stimulation, so something cold becomes colder, there is a high risk that you actually suffer from injuries from the cold. So human beings are way more likely to have injuries from coldness, freezing limbs, than from warmth, because we recognize a change in temperature upwards more promptly and stronger than in the other direction. That is the reason behind that. So these two go together. Okay, another problem of myself and probably many other people is the perception of sweetness. One fundamental problem here is that with age it is reduced. So you might experience elderly people using a significant amount of sugar to make for example, tea or coffee sweet, and that has something to do with the reduced perceptibility of sweetness and actually of all gustatory stimuli with age. So this is rather a physical problem. But the other thing is that you can increase the sweetness of something, like for example a drink or something to eat, and the perception will only grow underlinearly. So we are going now towards the logarithmic scale. That means it becomes sweeter and sweeter and sweeter, and therefore unhealthier and unhealthier, but you don't perceive it. Beyond a certain level, it doesn't make much difference anymore. That is a logarithmic problem. Of course, it has an effect on your body because your body has to deal with those carbohydrates. Yeah, the effect is, I think, clear to everybody. Okay, the classic logarithmic scale is loudness. We also come to that, and there are others who are even more logarithmic. So we have a strong flexibility in handling them. One, for example, is viscosity. I think defined again as putting something hardly liquid on your palm, changing the chemical structure of that thing, either by making it warmer or, I don't know, adding some water. I don't know the details. However, you will hardly notice a difference. If something has a certain amount of viscosity, it is perceived in a particular way. Sorry. If that level of viscosity changes, only very little is perceived. That is apparently a haptic stimulus that has hardly any psychological relevance for the human brain. In general, we can say the higher Stevens exponent is, the more relevant apparently our brain considers the stimulus for us, for our survival. Electrical shock, very bad. Having to use an excessive amount of muscle force, very bad thing. Overheating or burns, very, very bad thing. Coldness, not so bad. Still bad, but not so bad. Sweetness, in the old days, something that seldom occurred. Sweetness revolution started about in the 16th century, had to do with the expansion over the oceans of the Europeans and so on. It's a long story. So evolutionary irrelevant, and the same for loudness and viscosity. Okay, so much on Stevens exponent and on psychophysics. If you want to keep something in mind, which you should, otherwise you're wasting your time, keep in mind Stevens power law. It is very interesting and it allows you to understand in a systematic way something fundamental about human nature that is hardly ever mentioned actually in educational programs. Okay, now I would actually like to go into a long dive of aspects of how our vision and how our oral sense actually work. The first one is the visual sense, and then we go to hearing. In the visual sense, this is one of the figures from my handbook of multimedia information retrieval. As I said in a couple of other lectures, the handbook is available for free from the e-learning platform. It is slightly outdated when it comes to deep learning because I wrote it in 2011 and 2012, but all the classic methods of feature engineering and most of the other machine learning constructs that we use are still up to date. So feel free to have a look at the book and use it in whatever way you like, except of course plagiarism. Okay, so what do we have here? We already spoke about the eye. Relevant parts there, physically relevant, is the lens, of course. In the background, we have the retina for the perception of brightness. And in the center, we have the fovea for the perception of color in the really sharp area. Eyes come in pairs of two, which allow us to, through the disparity, to compute the distance of an object further down. 3D processing is not really our topic here in this lecture. There are specialized lectures on that at TU Wien. The information then goes to the thalamus, and there is a so-called optic radiation that goes back from the central area of the visual cortex. The visual cortex is probably the best investigated area of the brain. We will go through the details next. This was, for example, done in the 1960s in experiments by the later Nobel Prize laureates Hubel and Wiesel. The experiments found a lot of interesting information. However, many scholars and ordinary people, or non-scholars, let's put it that way, today consider their methods sometimes a bit rough or actually downright brutal. They would, for example, use monkeys and insert lenses, metal lenses, into their brain in order to record action potential from the neurons. That was possible in the 1960s. It is very hard today with ethics commissions. It is true that we learned a lot through these experiments, but they were very troubling also for many other people. So this is an active discussion on what is ethically acceptable and what isn't. If you would like to discuss that, you can also use the forum, or you can join us in my Media and Brain 1 and 2, where we go a little bit deeper also on the ethics of neuroscience, but of course only very briefly, since we are doing technical lectures. I just wanted to mention it. Here we have a well-investigated area, but the methods that were used appear to many people today questionable. Okay, just one little add-on. There is a blind spot in the fovea, or in the retina, because that is where the optical nerve goes out into the brain and eventually down to the visual cortex, from which the information goes back forward into the so-called optical radiation. That means that visual perception is centered here in the visual cortex, but influences a lot of other areas, apparently. Okay, so this is essentially the situation. I told you that we have an Rgb perception system. Maybe let's put that one first. What does Rgb mean? We add 3 color channels based on the so-called 3 stimuli theory. Three channels, red, green, and blue, are sufficient to build all the colors and construct all the colors that are relevant in nature in order to distinguish objects. I already also told you that color perception is a goodie, more or less. In computer vision, we mostly work with the brightness alone, because when it comes to optical information, we are interested in the edges, in the changes from one brightness level to the other. That gives us shape information, and shape is the essential for visual semantics. However, having color is still a nice thing to do. If you watch the telly, you're usually not satisfied by just seeing in black and white. Color perception is very satisfactory for us, for the psychophysical process. Okay, in practice, I also told you that other color models than Rgb are more useful, like the CEA space, XYZ space, that distinguishes more green tones than, for example, yellow tones. Why that? Because green evolutionary has been more important for us, and we are able to distinguish more green shades than yellow ones. So, how does it work? We have 3 different types of cones. This is another slide from the book. Blue is well set off. It goes to 420 nanometers in the peak. Green is at 534 and red is at 564. Apparently, the space between green and blue is very, very short. It's just 30 nanometers when it comes to the peak, and therefore there's a high overlap between the 2 functions. And that, of course, if your individual optical system, because these are averages over populations, is slightly different, it might happen that the 2 peaks are actually overlaying, are going together, and that would mean for you that you don't have a 3rd channel available anymore, that you can distinguish certain colors, but not the full scale of different colors, not the full spectrum, because they are so close. What scientists say is that the green cone and the red cone are evolutionarily the same, and the red cones only split off very recently in development. Okay, Fundamental thing, of course, is it all depends on the wavelength of the light that comes in, which is again influenced by the surface of the objects that were touched since the photons came from the light source, in our case mostly the sun, and eventually hit the retina or even the fovea. Okay, from this slide, and this is one of the slides that takes photos from the book of Kandel, Schwartz et al. Neuroscience. It's enormous work, highly interesting to read, highly recommendable. And the slides were done by one of my students in an earlier year seminar by Mrs. Katrin Lasing. Okay, what I wanted to show you is it shows the same picture again that we had before. We have the optical nerve coming out of the eyes, we have the visual cortex in the back, and we have the radiation to the front. What I wanted to show you here is that a first step of processing, and that is very interesting, is edge detection in the visual sense. So when I said before it is about finding these areas where we have a dramatic change in brightness in order to define the shape of something, then the on-off center cells, the ganglion cells, are actually doing that. That is what I wanted to say. And how do they do that? They do it in a two-step process. There is the optical information coming in, maybe from RGB, or in a form of luminance coming from the rods. And the first thing they hit are so-called bipolar cells. These come in two shapes in the retina. There are bipolar cells in other parts of the brain as well, but retina bipolar cells, all bipolar cells can trigger an on-off state depending on their input. So there are bipolar cells that have a strong firing pattern from the input side and create an off, the other way around, or they can go just through. That means an off bipolar cell means that you have no input signal but create an output. Such a thing is also sometimes termed a tonic neuron, or I think the experts also say a graded output. Okay, meaning that we can create a signal where there is no input from the input side. And in the third stage, so first stage reception, second stage bipolar processing, and third step is then the ganglion cell, retina ganglion cell. And what does it do? It connects neighborhoods and looks for patterns such as this one. This one shows on cells in the neighborhood and off cells in the center. And that means we are looking for an edge that looks like this. Where the outside is on and the inside is off. So this information comes with two aspects. One is apparently an angle and the other one is a length. In the length, two fundamental lengths are distinguished. One of them is within the fovea, and the other one is outside the fovea, so longer than the fovea. Angles are distinguished, I have forgotten, sorry, I think it is something between 3 or 5% of different. So we have, as one of the earliest processing stages of the visual system, a layered structure, center structure, neighborhood structure, and processing of the entire visual field for short edges and long edges in different orientations. So what we're doing, if you remember from Similarity Modeling 1, texture and shape features, we are actually performing an edge detection as one of the first processing steps on the luminance channel. As told you, color is not relevant for that part of processing, which is quite intriguing. That is quite intriguing. Okay, so here we have another picture of what is going on. We have different lengths and different orientations. That comes from MPEG-7. I told you in the lecture on feature engineering, this is a standard defined in the late 1990s for extraction methods from audio and video. So the artificial variant to the psychophysical process. And there it is a feature called texture histogram that employs this finding about the ganglion cells. Retina ganglion cell, to be more precise. There are ganglion cells somewhere else, and ganglion cells always summarize small neighborhoods in order to create some output, which is an intriguing finding, I believe. So let's have a general look. This is another one from Faulasinger, based on photographs from the book of Kandel et al., with hopefully sufficiently low quality not to violate any copyright laws. I want to show you with this slide how extremely complex the visual processing is if you look at this wire diagram. Otherwise, nothing much can be identified. So let's go into a bit more detail. The visual cortex, so this back part here of the brain, consists essentially, or triggers essentially, two different pathways. Both of them start out in the occipital cortex and then go into one direction or the other. One is the ventral pathway and the other one is the dorsal pathway. The ventral pathway stands for the what system, and the dorsal pathway stands for the where system, if I remember correctly. Let's have a short peek. Yes, exactly. That's the distinction. So ventral pathway means object recognition. Dorsal pathway means motion recognition, location recognition. It is intriguing to see that what we had in feature engineering, we apparently also have here in the area of the natural brain. Of course, our findings on the human brain and our work in signal processing happened basically at the same time. They sometimes influenced each other, so that, for example, also neuroscientists would start with hypotheses from signal processing. That is something you can read in Kandel and Schwartz et al., for example. But many methods were also developed and identified independent of each other. Okay, that is the processing in the visual cortex. So let's have a closer look. What happens in the first stage, in the occipital cortex, before we go into ventral and dorsal, another one from Faulasinger. Edge processing, we already have seen. This is something that is done by the ganglion cells. Another interesting aspect here is the processing of color blobs. Blue blobs with yellow environment. The other way around. Same with green and red. So fundamental object shapes are here identified. In the next step, more complex processing happens. Here we have, for example, the Gestalt laws. Textures are identified. These contours are built together into an object. Therefore, we might have contours that do not exist. So optical illusions happen here. That is already directly behind the edge processing, you have to think. So this is on a relatively low semantic level. Which is very intriguing. Then we have a lot of luminance invariant processing. So the hue needs to be converted. We are like going from Rgb to U saturation and value or some similar processing models. Just like we do in computer vision, we also do here. And that comes only after the Gestalt processing, which is kind of interesting. And then already comes motion detection, 3D vision, and direction processing, which is a semantically higher level. So what happens here is a step-by-step, layer-by-layer process of semantic enrichment. Low-level features are used to compute more high-level information. Edges, Gestalt features, U values, movement features. And how is it done? By the individual processing of the neuron, which is convolution. Okay, we come to that also a bit later. Good, let's have a look at the ventral system. I told you it's the what system, so it's about the object detection. And after the processing in the ventral pathway, we are able to distinguish objects by their type. So it doesn't matter anymore if we see the cat from the side, from the back, or from the front. We already recognize the concept of the cat or whatever type of object we have. So that happens quite early, just like in the deep neural networks. We are able to distinguish different sizes, positions we are position invariant. And we might even have occlusions. So there might be a banana in front of the cat or in front of the tomato here, whatsoever, but we still recognize the object. That is what the ventral pathway does. And that is also what today a convolutional neural network actually can do to a satisfactory degree. So we solve this problem, the whole ventral pathway as well. When it comes to the dorsal pathway, so the where system, things are way more complex. We come to motion on the next slide. Again, this is a slide by Vorlasinger. Since we have self-motion involved and object motion, we have a number of degrees of freedom that need to be aligned together. The position in space of the skull, the position of the body, the speed of the body movement, and so on. It appears to be the case that also the brain computes kind of an optical flow, so the objects are tracked. And it appears to be that disparities between the eyes are also exploited in order to do object position, in particular when it comes to depth. However, significantly less is known about the dorsal pathway than about the ventral one, so we don't know fully how it happens. We just assume that it is a form of optical flow tracking that happens in this radiation of the brain coming back from the starting point that was the visual cortex. It highly interacts with different types of other centers, with different objects, even with other senses. Therefore, it's not so clear and not so easy to define what actually happens. Now, let's go through a few examples, color, shape, and movement of how it actually happens as far as we know. We continue with seminar slides. First thing for sure is Rgb processing. Then we obviously have a processing of this yellow and blue, so of the so-called opponent cells of red and green that are in different positions of the spectrum. Then there is a form of object tracking in the next step. I told you that the U is encoded in some form, and this is then added to other object features. This appears to be the process that happens in the brain, independent, of course, of the edge processing that comes on the next slide. So here we merge, and here we compute U, blobs, opposite colors, and start out with the Rgb receptor cells. Okay, color processing, just like we do color features in the old-fashioned feature engineering, and implicitly, of course, as well in a modern convolutional neural network. Shape processing starts out with the ganglion cells, bipolar and ganglion. Then apparently we distinguish the length and the angles in order to form something like texture. In the second step, these are then merged to objects. Missing lines in the shape are interpolated. That leads us to something like the Gestalt laws. So this happens very early. Another finding by psychologists was that then we have a processing step where we approximate entire objects by so-called curve points or interest points. This is something to which we come when we speak about spectral features in a later video. And again, then comes the merging. So apparently we follow a processing queue very similar to what we also use in computer vision, by doing first simple edge detection, texture recognition, which means patterns, repetitiveness, a bit more semantics, object recognition, and eventually merging with others. Last example that I want to show you before we have an excursion to the neuron, and from there go on to hearing, is motion. As we said, we have to distinguish the motion of the observer from the object motion. All of them have a lot of degrees of freedom, and this is done in the dorsal pathway. And it appears to be that there are something like motion gradients, so that we can, for example, recognize our own movement as a form of camera motion. Just the way I explained it to you, when all optical flow vectors go into the same direction, then apparently we are moving in the opposite, just as the camera would move. And we are able to distinguish forms of direction and differential movement of different objects as we think, or the neuroscientists think, by a form of optical flow, which is based apparently on simple objects, not like, there's probably a difference, probably not like macro blocks in computer processing. So probably there's a bit more semantics. But I say a lot of it appears to be, or I believe, somebody else said, believe, so little is known when it comes to the field of motion. Apparently, motion is more complex than, for example, vision. Why could it be? Because our vision, because our color detection or edge detection, because it's probably non-local. So it's not in one particular spot in the brain, because motion genuinely means to go from one area to the next, visually, and therefore probably due to the architecture of the brain, we necessarily have different centers involved in order to be able to handle that. Okay, having done that, let's do the neuron. I should have done it before this block, but I simply forgot. We had it before. You remember that the center part of a neuron is a block that consists of two components. The nerve center. One component is the soma, the other one is the axon hillock. After that comes the axon, so to say the cable channel, and that fades out into different synapses. On the input side, the soma bundles different dendrites. Okay. Dendrite 3 means that these are the nerve ends on the input side. The input is then propagated to the output side in a multi-step process. As I said before, the soma is responsible in this process for actually providing the neurotransmitters. And so it makes it function, makes the neuron function. And secondly, it bundles the inputs. The actual depolarization, so the creation of an action potential, is done in the axon hillock. It is an electrochemical process. The incoming potentials open gates. The gates allow the entrance of some ions, and the ions cause another reaction that free an electron again. Okay. In the average case, not all neurons are spiking neurons. Others are, for example, tonic, meaning that they have a more relaxed firing pattern, or fire all of the time, or even fire when no input comes along. I told you the closer a synapse gets to the axon, the stronger its influence is, and synapses, we said, can either be positive or negative. Positive means excitatory, or inhibitory. Okay. Inhibitory means that they actually reduce the action potential, which is another important function. Okay, what does the axon do? The axon propagates the output. The bigger the axon, the faster it goes. And the second, it isolates, it insulates from the environment in order to not to have interferences of the different signals. Synapses connect to dendrites. And therefore we have a network. If you think of the artificial alternative, then the function of axon and soma are actually to summarize and to compare to a threshold. The function of dendrites on synapses is to weight. We have positive and negative. That is something we often don't have in artificial networks, negative weights, so that they might have a negative influence, and the propagation process is just a layer structure. Of course, there are many degrees of freedoms in the brain. There are different types of neurons. The architecture is different for interneurons versus receptor cells versus motor neurons. We are here dealing mostly with the interneurons. The other ones are not interesting in the context of our lecture. So there are really many degrees of freedom, and this is just the basic architecture. Okay, having said that, let's return to our psychoacoustic processing and psychophysical processing and continue with the ear. The ear consists of the outer ear, the mid-ear, and the inner ear. The ossicles in particular are important, and the eardrum for the propagation of the signal and the amplification. The ear canal even has a function. It acts as a filter that maximizes signals of, I believe, 1000 Hertz. Okay. The most important part, however, is the cochlear organ. In the cochlear organ, what we have in terms of first a sound wave, so an air wave, is transformed into a liquid wave because it's filled by a liquid, and eventually into electrical current that is propagated through the brain. That process happens in the cochlear organ. So let's have a look about how it happens in general. This figure is another one from the book. As I said, also the slides with the figures alone can be found in the e-learning environment. So what happens? In the cochlear organ, we have so-called hair cells. These are groups of cells with approximate the same length. It's actually the structure of a stair, but that is a detail we can omit here. The shortest hair cells are on the outside. And in the center, in the apex, we have the longest ones. The whole thing is filled by a liquid. And therefore, the air wave incoming is transformed into this liquid wave, and the hair cells move in the liquid with the incoming wave. The shortest cells at the beginning will move with a higher frequency given the same amount of pressure than those in the apex. The longer, the more the incoming force can be distributed over an edge, and therefore less movement should be the outcome. So we should have a lower frequency for the longer edges and a higher frequency for the shorter ones. You probably already guessed it. The hair cells, the groups of hair cells, are the actual receptor cells in the auditory nerve. So the incoming wave is transformed through the movement of the hair cells into electrical signals. And on the outside, we have the high frequencies. For purely physical reasons, and the low frequencies are in the center. That distinction is to a degree important for our everyday life, because it means that the lower the sound, the harder reception can be triggered, because we lose, of course, energy on the way into the spiral of the cochlear organ. Since we lose that, we need a higher amount of energy in order to be able to hear low frequencies. We come to that on the next slide. Now, how is the propagation done? The hair cell contain ion channels at the top, and these are connected. These channels are connected from hair cell to hair cell over so-called tip links. As far as I know, but I'm not an expert, this is actually a physical connection. That is, by the way, the reason why you can actually break your hearing, because these tip links can break. They will break on too high pressure coming in. So if you hear music too loud at a concert or with your earphones, you might actually break your tip links. If they have been open at that time, you might experience a so-called tinnitus. That is a constant transformation of chemicals into electrons. In this case, it's potassium ions that enter from the liquid into the hair cell if the tip links open. And inside the cell, there are different chemicals. The potassium reacts with those, and in that process an electron is freed, which is then propagated to the brain. So let's have a look at it again, because it's a very important process and we will re-encounter it when we speak about the Fourier transformation. We have an incoming air wave. It's transformed into a liquid wave. Inside the liquid, hair cells move. They are organized in layers, short ones, medium length, long ones. Short ones will have a higher frequency when oscillating than the long ones. So these are receptive to a certain frequency, and depending on a different form of length, they are receptive on others. It also depends on the amount of energy of the signal. The wonder happens in the cell, where chemicals are transformed into electrons. Hair cells are connected, mechanically connected. Ion gates open. Chemical reaction causes propagation of electrical signal. And that is also the reason why we can do with the 10 by the power of 4 connections, because these hair cells provide us with the means to sort out different frequency. So what the cochlea does is it does frequency analysis. Transformation. In an almost perfect way. Okay, so this is the nutshell version of how the inners of the ear works. Now, what aspects and what effects does this process cause? Let's have a look at that. One thing is that we can distinguish different levels of loudness. We have an absolute threshold of hearing, meaning that below that we cannot hear anything. Everything is of course individual, but if you average over entire population, then this is about where you will end. This is one of the figures taken and modified from the book again, as far as I remember. On the other end, on the top level, beyond a certain threshold, we have a threshold of pain. We experience pain because tip links break, no? Or there's a high stress on the hair cells. Hair cells. So this is where we actually perceive pain. Why? Because our physical system makes us perceive this pain in order to shelter us from permanent damage of our hearing system. Okay, the lower threshold is physically defined if the energy in the signal is insufficient to trigger the hair cells. As you see here, because we have the frequency on the horizontal axis, our threshold of hearing depends on the frequency. So it's different for the smaller hair cells than for the bigger ones. What does it mean? At 4000 kilohertz, those are situated very early in the cochlea, we hear best. This is conveniently the upper end of our voice mechanism. So we are optimized for hearing voices to a certain degree. Below that, we have a very good sense of hearing, in particular in this area. Only in the lowest part, we have a very bad one. Please note that this is logarithmic scaled. Okay, that means the energy has to be very high. If you want to hear bass sounds, because they come so late in the cochlear organ. I could imagine this is another thing that is evolutionary, because we simply didn't need it in the old days to distinguish possible predators, for example. Today this causes a big problem. If you are giving a party and you turn up the music, then these bass parts play an important role, for example, for rhythm detection in dancing and so on. However, due to their high energy, they also easily penetrate the walls to your neighbors, which hear only this part, but don't hear the higher parts of the sound signal anymore, and then don't perceive what you perceive as music, but perceive it as noise. And they hate noise, of course, due to the high energy that is what arrives in their place. So if you give a party, please think of your neighbors and tune the equalizer so that you can do with low levels of bass signals, if somehow possible, because this is how we perceive. This is the area of speech perception. Music perception is better for the simple reason that an orchestra of different organs can play more complex, instruments can play a more complex aggregation of sounds. Okay, so these are the simple hearing thresholds. There is a nonlinear relationship, as we said, between the sound pressure and the loudness. That means below a certain loudness, below a certain sound pressure level, we don't hear anything, and only then it cranks into an actually exponential function. That means if you increase the sound pressure, loudness will go up over linearly. This is again logarithmically scaled. Okay, let's leave it here. So, and just a conclusion on that, maybe one is that if you compute the root mean square, as I showed you in the lecture on feature engineering, you could employ this loudness function and thus compute a psychoacoustic loudness. That would be a simple way of actually increasing the quality of your output, because not every root mean square means the same actually. Very important function is the so-called Mel curve. We will encounter it when we speak about spectral features. It defines the relationship between the frequency, that is physically actually the case, so this is a physical stimulus in our psychophysical system, and the perceived pitch. So this is a psi here. How does it work? We have, until a certain frequency, an over-linear increase in perceived pitch, that is the highness of the sound. That means you increase the frequency a little bit, and we as human beings would judge, oh, this was a significant increase, I noticed the difference. Beyond that point, that is defined as frequency of 1 kilohertz, has a Mel value of 1000, Mel is an artificial value, for this perceived pitch. Beyond that level, it goes into a logarithmic scale. That means you increase and increase and increase the frequency, but the perceived pitch only goes up little. So our hearing beyond 1000 Mel becomes less sensitive. It is excitatory below and less excitatory beyond that point. That is the Mel curve. Very important if you do frequency processing. The so-called Mel substral coefficients that are the fundament of most speech or sound applications heavily employ this function. We come to that again when we speak about the spectral features. And maybe, sorry, one last thing is, it is not a purely logarithmic function. It is mostly a logarithm, but it has a lot of magic numbers for the constant and for the Stevens exponent. Okay, the last function from the psychophysical world has to do with a phenomenon that is known as masking. Masking means that if you hear two sounds that are close together in their frequency, and one of them is significantly louder than the neighboring one, then this one will mask out the others. It's a very complex phenomenon. It depends on what frequency you're dealing with. It depends on the relationship between the two sounds concerning their sound pressure level, and then gives you a two-dimensional curve. So the masking pattern is not the same for mid-range sounds as this one, as it would be for the bass signal, nor for the high frequencies. It's actually a whole array, a table of different masking effects. These are very important, for example, in audio transform for compression such MP3 and AAC, where signal components that can anyway not be heard by the vast majority of the users, non-expert users, are simply eliminated and not used for encoding. Okay, that is called the masking effect of audio. One generalization of the masking effect is the Barkhausen transformation, or are the Barkhausen bands, the so-called critical bands. The Barkhausen scale does, in a very complex formula, as you can see here, create a grouping of, in the event, 25 bands. Usually only 24 are denoted, but there is a default band, which is the 25th. And within such a band, masking effects occur highly. It is said that for the average listener, in that frequency band, and this goes over frequency, it starts at a particular frequency and ends at a particular frequency, masking effects are very strong. That means if you have one sound in that area and the second one, it is sufficient for you to process only one of them. You will see that when we come to rhythm detection in spectral features, this feature is heavily exploited. It is always any processing of the frequencies, for example, for timbre recognition. Timbre recognition can then be used for instrument identification in music recognition. We will always first employ the Barkhausen bands, and then on each individual band do the feature computation, because they are different from each other, should be treated separately, but everything that is within a band can be summarized more easily. That is the Barkhausen scale. Okay, that brings me more or less to the end of my lecture on psychophysics and perception. Just a few tiny notes maybe. We spoke about sometimes about human voice. You might want to memorize that this is a so-called source filter model. Meaning that with the power of the lungs, we create a source in the voice box, and then in the mouth, we filter different subsignals and build phone names and formats and so on. So that is for voice. That's the biometrics of voice, if you like. Similarly or analogously, for face recognition, usually this is done in a biometric way by computing in particular points such as the naseon or the nose tip, inter-eye distance, and compute these distances. These are typical local visual features, while as voice features are global or holistic. Just as a reminder. One last thing is, we have lots of patterns in the brain. From the smallest ones, such as the bipolars and the ganglion cells, going up to entire centers as the areas we saw in the ventral dorsal pathways, and going up to big so-called complex pattern generators in, for example, in the cerebellum. If you're interested in that, please come back to Media and Brain 1 and 2. In the summer term, there we deal with that in detail in order to identify traces based on natural processing in artificial neural networks that would give us something like artificial consciousness. Okay, to sum up, what did we do today? I gave you a lot of facts about the brain. Of course, you will not be able to keep all of them or only a small subset. Some of them might be interesting, such as the efficiency of the oral sense, the aspect of vision as being a local operator versus oral being a global holistic operator. I think we did that to a sufficient degree. Secondly, you should understand the basics of psychophysics. Here, the most important aspect is that what you perceive is not what is physically happening. That is very important. And the way to describe that in a uniform way is Stephen's power law, with Stephen's exponent being defined for thousands of different forms of stimulation for the brain. Eventually, we did a lot about how processing actually works in the brain for vision and for hearing, and in particular went for the big audio transformations, going from sound pressure to loudness, going from frequency to perceived pitch, and distinguishing the critical bands with the masking effects. All these three inputs and this foundation will be used in the next lecture block on spectral transformations and on integral transformation for identifying good summaries, good models for similarity judgment, similarity processing, in order to increase the semantics of feature recognition and of media understanding. Thank you very much. I hope you enjoyed this lecture. If you have any questions, please state them in the TU Wien forum. The link is given at the end of the video and in the TU Information Systems.